Hello students, welcome to the subject of complex variable and partial differential equation. Myself Dr. Ankit Acharya, and in last lecture we discussed about case 5 to find particular integral for homogeneous linear partial differential equation. So now we discuss in today's lecture about non-homogeneous partial differential equation. Now what is the meaning of non-homogeneous? That means, see, the linear partial differential equation which are not homogeneous is called non-homogeneous. That means all the terms do not contain derivative of the same order, right? Up to this we discuss about homogeneous partial differential equation, homogeneous linear partial differential equation, in which all the terms contains derivative of the same order. But suppose all the terms do not contain derivative of the same order, then we can say that it's a non-homogeneous linear partial differential equation. For example, you can see that this is del square z by del x square. So this is d square. This is also d into d dash. So order is 2 for first two term. Now here you can say that del z by del x. So this is d, del z by del y. So this is d dash, right? So all the terms does not contain have same order. So that's why this is not a homogeneous partial differential equation. So again, this is d square, d dash square, this is 2d plus 1. So this is not homogeneous. Okay. And for non-homogeneous linear partial differential equation, you have to follow some rule to find complementary function. Okay. So these two are definition, reducible and irreducible equation. Suppose if the operator f of d dash can be expressed as a product of linear factor of alpha d plus beta d dash plus gamma. Suppose we can express our f of d dash in this form in a product of linear factor of alpha d plus beta d dash plus gamma with alpha beta gamma but of base constant, then we can say that f of d dash is a reducible operator, or we can say that f of d dash into z, that is equal to f of xy, which is our partial differential equation, is called reducible equation. And for reducible equation we can find complementary function. Okay, so these are the method. For example, let's try to understand some of the examples. See, 2d minus 3d dash plus 1 into z, that is equal to 0. So definitely f of d dash is 2d minus 3d dash plus 1, right? Definitely this is not a homogeneous because last term is a constant. Okay, so this is not a homogeneous, but this is a reducible operator because alpha is equal to 2, beta is equal to 3, and gamma is a constant, gamma is 1. Okay, here also this is d square minus d dash square plus 2d minus 2d dash. So definitely this is not a homogeneous partial differential equation, but we can convert this non-homogeneous partial differential equation into a reducible operator. So first of all, first two term is d square minus d dash square. So just simple simplification, d minus d dash into d plus d dash plus 2 common from this two term. So plus 2 into d minus d dash. So d plus d dash, okay, plus 2, d plus d dash plus 2, and in bracket we have d minus d dash. This equation 3d square minus 5d dash into z, that is equal to sin x. Now this is not a reducible equation, so this is called irreducible. Okay, now for reducible equation, for reducible operator, we can find complementary function, and for that we have to follow this rule. So consider this equation f of d dash into z, that is equal to f of xy, and the auxiliary equation f of d dash, that is equal to 0. So method 1, f of d dash is reducible, right? Now if alpha d plus beta d dash plus gamma is a factor of f of d dash with alpha not equal to 0, so consider alpha not equal to 0. So in that case complementary function, that is e raised to minus gamma upon alpha into x, f of beta x minus alpha y. Okay, so you have to follow this rule to find complementary function. Now sometimes the degree of alpha d plus beta d dash plus gamma is more than 1, so for that we have to apply case 2. So if alpha d plus beta d dash plus gamma raised to n is a factor of f of d dash with alpha not equal to 0, so for that we have to apply this rule, e raised to minus gamma upon alpha into x, f1 beta x minus alpha y plus x into f2 beta x minus alpha y plus up to x raised to n minus 1 fn beta x minus alpha y. Okay, now sometime what happen, alpha is equal to 0. That means what? Only beta d dash plus gamma is a factor of f of d dash. So for that you have to apply case 3. Okay, let's see. Case 3, beta d dash plus gamma is a factor of f of d dash with beta not equal to 0 and alpha is equal to 0. So for that, complementary function is e raised to minus gamma upon beta y f of beta x. Okay, so now instead of x, now here we have y, and instead of alpha in denominator, previous case in denominator we have alpha, but in this case in denominator we have beta. Okay, because alpha is equal to 0, so that's why. So now you easily you can remember, right? Now if beta d dash plus gamma raised to n, that means degree of beta d dash plus gamma is more than 1, then we have to apply this rule. Okay, complementary function, that is e raised to minus gamma upon beta into y f1 beta x plus y f2 beta x plus up to y raised to n minus 1 fn beta x. Okay, so let's solve some examples for non-homogeneous linear partial differential equation. So this is my first example. D square minus d dash square plus d minus d dash into z, that is equal to 0. So clearly f of d dash is not a homogeneous operator, right? So d square minus d dash square plus d minus d dash, that is equal to 0. Now from first two terms, d square minus d dash square, I can write d minus d dash into d plus d dash, and this d minus d dash as it is. So this can be expressed as a product of linear operator. Okay, as a product of linear operator in the form of alpha d plus beta d dash plus gamma. Let's see, d minus d dash is a common, so d minus d dash is a common term. So now we have d plus d dash plus 1, that is equal to 0. Okay, that is equal to 0. Now, so that's why for first linear factor, what is my alpha beta gamma? So call it, for first linear factor, call it alpha 1 beta 1 gamma 1, and for a second linear factor, call it alpha 2 beta 2 gamma 2. Okay, so we know that alpha is a coefficient of d, beta is a coefficient of d dash, and gamma is a constant term. So alpha 1 here, alpha 1 that is equal to 1, beta 1 that is equal to minus 1, and gamma 1 that is equal to 0. Okay, and alpha 2 that is equal to 1, beta 2 that is also 1, and gamma 2 that is also 1 for a second linear operator. So you can easily write down the complementary function. What is the rule? E raised to minus gamma upon alpha. So for a first linear factor, I can write e raised to minus gamma upon alpha, that means 0 upon 1 into x f1, okay, beta x minus alpha 1. So minus x minus y. Clear? And now plus e raised to, once again, minus gamma upon alpha, so minus 1 upon 1, so minus x. Okay, I can write e raised to minus x f2 beta x minus alpha y, so I can write 1 into x, so that is x minus y. Now easily you can simplify, this is e raised to 0, which is 1. So the final answer is f1 minus x minus y plus e raised to minus x f2 x minus y. Okay, and particular integral is definitely 0 because right side we have a function 0, and the general solution z is equal to complementary function plus particular integral. So let's solve one more example. So d plus 2d dash minus 1 into 4d dash minus 3d plus 2 into z, that is equal to 0. So clearly for a first linear operator, what is my alpha beta gamma? Alpha 1 that is 1, beta 1 that is 2, and gamma 1 that is minus 1. Now don't forget, alpha is a coefficient of d, beta is a coefficient of d dash, and gamma is a constant term. So here we have 4d dash minus 3d plus 2. That means what? Alpha is minus 3d. Okay, don't write 4. Okay, so alpha 2 that is equal to minus 3, beta 2 that is equal to 4, and gamma 2 that is equal to 2. Now directly you can write complementary function. So the complementary function, that is e raised to minus gamma upon alpha. So e raised to minus 1 upon 1. So minus 1 upon 1 into x f1 beta x minus alpha y. So 2x minus y plus e raised to minus gamma upon alpha. So minus 2 upon minus 3 into x f2 beta x minus alpha y, so 4x minus 3y. Okay, so minus minus plus 3y. So when we simplify this term, that is e raised to x f1 2x minus y plus e raised to 2x by 3 f2 4x plus 3y. Okay, so this is my complementary function, and here also right side we have a 0, so particular integral is 0, so you can directly write general solution z is equal to complementary function plus particular integral. So the next topic of this chapter, and this is the last topic of this chapter, that is classification of second order partial differential equation. So you can see on the screen that the general form of second order partial differential equation is f of xyz pq rst, that is equal to 0, where x and y are independent variable, z is a dependent variable depending upon x and y, p and q are first order partial derivatives. We know that p is nothing but del z by del x, q is nothing but del z by del y, where r, s and t are second order partial derivatives. R, that is equal to del square z by del x square, s, that is equal to del square z by del x del y, and t, that is equal to del square z by del y square. Okay, so this is the general form of second order partial differential equation, and consider the second order partial differential equation. Capital R, that means capital R is a function of x and y del square z by del x square plus capital S into del square z by del x del y plus t into del square z by del y square, where capital R, S and t are function of x and y, plus any function of x, y, z, pq, that is equal to 0. Okay, or the same equation you can use standard notation, that means instead of del square z by del x square, okay, instead of del square z by del x square, here I use small r. Instead of del square z by del x del y, I can use small s, and del square z by del y square I can use small t. Okay, so the same equation we can write with this manner. Now the important thing is that you have to remember that this type of second order partial differential equation, okay, is said to be hyperbolic if s square minus 4rt greater than 0. So you have to remember all this formula. Okay, parabolic if s square minus 4rt equal to 0, and elliptic if s square minus 4rt less than 0. Okay, so you have to remember this three important formula. That means suppose you have second order partial differential equation, and suppose you want to check that classification of that second order PDE. So for that you have to remember all this formula. That means if the value of s square minus 4rt greater than 0, then it's hyperbolic. If value of s square minus 4rt equal to 0, then it's called parabolic partial differential equation. And if s square minus 4rt less than 0, then we can say that your partial differential equation is elliptic. So let's solve some example. So this is my first example. Classify the following partial differential equation. Now here you can see that del square u by del t square, that is equal to c square del square u by del x square, where c greater than 0. Okay, now rewrite the same equation with this form: c square del square u by del x square minus del square u by del t square, that is equal to 0. Now here instead of x and y, here we have x and t. Okay, so instead of y, here we have t, and u is a dependent variable. So you can understand that capital R, that is equal to c square, s, that is equal to 0, and capital T, that is equal to minus 1. Correct? Okay, capital R is the coefficient of del square u by del x square, so that is c square. Capital S is a coefficient of del square u by del x del t, so that is 0. And capital T is a coefficient of del square u by del t square, so that is minus 1. Now find out the value of s square minus 4rt. Okay, so that is 0 minus 4, the value of r, that is c square, the value of t, that is minus 1, and this equal to 4c square. And the value of c is already greater than 0, that is already given. So 4c square, that is greater than 0. So that's why we can say that the given partial differential equation is hyperbolic. Okay. So the given partial differential equation, just write down the full sentence. Here I just write down the only one word, that hyperbolic. Okay. But you have to write that the given partial differential equation is hyperbolic. Next example. Del square u by del x square plus del square u by del y square, that is equal to 0. So clearly you can understand that here r is equal to 1, okay, s is equal to 0 and capital T, that is equal to 1. So what is s square minus 4rt? The value of s square minus 4rt, that is equal to 0 minus 4, 1 into 1. So that's why this is minus 4 less than 0. So that's why you can easily understand that the given partial differential equation is elliptic. Now, del u by del t, that is equal to c square del square u by del x square. So here just write down this equation with this form, c square del square u by del x square minus del u by del t, that is equal to 0. So clearly you can understand that r, that is equal to c square, s, that is 0, s means what? Coefficient of del square u by del x del t, okay, and t, capital T, that is also 0, because here there is no term of del square u by del t square. So capital T, that is also 0, capital T is nothing but coefficient of del square u by del t square. So clearly the value of s square minus 4rt, that is equal to 0 minus 4 r is c square, t is also 0. So the value of s square minus 4rt, that is 0. So that's why we can say that the given partial differential equation is parabolic. Okay. Now the next example. Del square u by del x square plus 3 del square u by del x del t plus del square u by del t square, that is equal to 0. So you can clearly understand that capital R, that is equal to 1, capital S, that is 3, and capital T, that is equal to 1. So the s square minus 4rt, the value of s square minus 4rt, that is 9 minus, okay, 4, r and t both are 1. So 9 minus 4, that is 5, 5 greater than 0. So we can say that the value of s square minus 4rt greater than 0. So that's why the given partial differential equation is hyperbolic. Okay. So using this method, you can easily understand that your second order partial differential equation is hyperbolic, parabolic or elliptic. Okay. So in today's lecture, we discuss about how we can find the complementary function if suppose your partial differential equation is not homogeneous. Okay, so for that you have to remember all this formula. And one more important thing that I want to tell you, that to find particular integral you have to follow the same rule, case 1 to case 5. Okay, suppose your differential equation is homogeneous or non-homogeneous. In both the case, to find particular integral, methods are same. That means you have to follow from case 1 to case 5. Either your partial differential equation is homogeneous or not homogeneous. Okay, so the method are same to find particular integral. And also in this is last topic in which we discuss about classification of second order partial differential equation. So this is the last lecture of this chapter, second and higher order partial differential equation. Thank you.